Hey all. So my name is Tony Nguyen. I'm a big data consultant for AWS. And today we're going to talk about how to migrate big data workloads to Amazon EMR. So going through the discussion we're going to have, I just want to focus on a couple of big things. The first thing is really the first step you should be taking when you're looking at migrating anything to EMR is how do you deconstruct your current big data environment on-prem or wherever it may be. You need to look at all the certain components of it, every specific kind of chunk that talks to each other to make sure that you have a full understanding of what you're getting into before you start migrating. The second part is identifying challenges with what you have today, right? You want to look at and identify which kinds of issues you're having with your current infrastructure, what you might want to fix, what you might want to improve. And then the third part is what components would you want to migrate to EMR? Which engines are right for the job? How would you build out the architecture? Very common questions such as how do you architect for cost and scalability? And one of the most important questions, in my opinion, is okay, how do we secure the cluster? And then we'll end up with customer migration stories, what customers have done in the space, and we'll end it with some Q&A. So let's talk specifically about deconstructing your current big data environment. So big data workloads are slightly different from typical migration projects because we deal with a lot of open source tools and applications. It's not exactly like take my code, change it, and modify your schema and deploy it in AWS. You've got to think about how you're going to deploy the infrastructure, how you're going to connect and stitch things together. And to do so, you really need to look at how you can deconstruct your current environment. So what does an on-prem Hadoop cluster look like in general? Well, they tend to have 12 cores, 32 to 64 gigs of RAM, and 68 terabytes of hard drive space. And that's about 3 to 4K per node. Now, that's not including, say, volume discounts. But in general, what you can do is kind of estimate the cost of an on-prem cluster by multiplying by the number of nodes at 3 to 4K. Another cost that you need to think about is networking. So switches are part of the cost because you still have to create networks, right? So you need to make sure that you take that into consideration when you're evaluating your total cost of ownership. Racks are also another component that you need to evaluate. One good thing is generally no SAN is involved in the situation compared to a typical migration project because the data is all local to disk. So that actually drops the cost down when you're looking at a Hadoop cluster on-prem. One thing is that most of these clusters have an open source implementation or fixed license from one of the popular distributions. These licenses tend to be attached to the nodes in the sense that where you have, say, 2,000 cores, you have a 2,000 core license. So it's pretty static in nature. It's difficult to, say, dynamically take away nodes or add nodes without dealing with more license issues. Another thing to think about is how Hadoop, it comes with a file system called HDFS. It, by default, has a replication factor of 3 times. So let's imagine if you had, say, 100 nodes at 6 terabytes each. That's about 600 terabytes of storage. You really only have 200 terabytes usable because of replication. So for those of you who are familiar with S3, imagine using S3 as your storage layer. That drops your cost down by 1/3 because in S3 you don't have to replicate. That isn't even the whole picture because your on-prem environment is likely to have its presence in a single data center versus S3 where it's a multi-availability zone solution. And by that means itself, your cost would drop down significantly from a storage perspective if you're able to use S3 as your storage layer during your migration from an on-prem environment. So the next thing to look at is, okay, what kind of workload types are running on that cluster? So let's talk about them. Let's just go down this list. So typically you have, say, large-scale ETL, maybe some simple transformation, or maybe something more complex. Typically, the same cluster that's running this ETL kind of stuff is using interactive queries. They might also be doing some machine learning, maybe some Spark ML, something of that nature, some search, maybe some Kafka, NiFi, Storm, something along that nature. But my key point is that these workloads tend to all be built on one single monolithic cluster because they all need to talk to HDFS. This is the most important thing to think about because we're going to talk about breaking free of this model and do what we call decoupling storage and compute. Or we put this in S3 and allow us to use each one of these components in a decoupled architecture. By co-locating data on S3, you aren't really restricted to putting this all in one architecture, and you can decouple and deconstruct. The next thing to think about is security. So how do you migrate your current security over to AWS? You don't want to lose what you have today. In fact, you want to, in theory and hopefully, gain even more security. So in the realm of security, there are a couple of things you need to consider. So there's authentication, say Kerberos with the KDC or AD, LDAP integration, local user management, maybe Apache Knox if you're using that. There's also Auth-Z, authorization, open source native, say Hive Server 2 or HDFS ACLs, Apache Ranger or Apache Sentry. And then there's also encryption you need to think about. So that's local disk encryption with LUKS, HDFS transparent data encryption, in-flight encryption for each framework. And that last part is actually really important because some frameworks handle encryption differently over, say, shuffles. And it's something that you need to think about when you're migrating over. And configuration. You need to look at different tools for managing your cluster. And these tools can vary based on the vendor. So the swim lane is a really, really nice way of visualizing your job scheduling for a given Hadoop cluster. And it's really useful because what it allows you to do is figure out how your cluster is being utilized and, more importantly, where it's underutilized. One of the great things about Amazon and AWS services is that you're able to spin up clusters and instances on demand. And you can spin them down on demand as a result as well. And being able to do this is really, really great because you can have your compute on when you need it, and you can turn it off when you don't need it anymore. So when you're looking at your current Hadoop cluster utilization, it's really important to see, okay, when we're moving to EMR, where we can actually do this sort of dynamic scale up, scale down, terminate when we need to, how can we best apply these concepts to making sure that we save the most money possible? The next thing is that the role of a Hadoop administrator is really, really hard. You want to make sure that we're not making it harder for the Hadoop administrator to do their job. So you need to make sure that you can manage the cluster, go through failures, hardware replacement, restarting services, expanding the cluster. You need to make sure that they're able to configure the cluster and make sure that they're able to still be able to tune it, be able to still tune specific jobs or hardware. You need to make sure that they can still manage dev and test environments. And you need to make sure that they still have the ability to easily and effectively back up data and have a means of going through disaster recovery. So let's go through these specific challenges that you may be running into when you're looking at your on-prem cluster today. So a very common issue is that your cluster on-prem is overutilized. You have lots of jobs running against it. People are competing for resources. They're being dumped into a queue, and they're basically fighting over the cluster. Having really, really tightly coupled storage compute requires buying excess capacity to what you have today. So you can't exactly right-size your cluster for your current load. You really have to buy excess capacity for what your current load is. And what this means is that you have idle capacity. During peak hours, you can be at perfect load, and you're completely underutilized the rest of the time. And what this means ultimately is that you're wasting money, and this results in high costs and really low efficiency. The next thing is management difficulties. So for instance, managing a cluster by yourself on-prem is pretty hard. You have to manage the applications, you have to make sure they're highly available, you need to ensure that there's durable storage and disaster recovery. If, say, you have HDFS and you need to make sure that there's a copy of that somewhere other than the cluster, what do you do? So there's a whole process that you need to think about when you're managing this cluster on-prem. Another concern is, let's say you have a team that wants to have a new framework on the cluster, or you need to do an upgrade on the cluster. These are concerns that are pretty important to basically every Hadoop administrator, yet it's pretty difficult to do on-prem. Having to go through an entire change process to put a new package on the cluster, or having to patch nodes out individually on the cluster is pretty difficult to do. It's frankly multiplied if you have multiple environments, right? It gets harder and harder if you, say, have a dev environment and a test environment and a production environment, all of which you need to manage and perform these upgrades on and add new frameworks to. So you can't do this by yourself. You effectively need a team to manage this cluster and procure hardware. It gets to be pretty complex. So with all that said and all those components in mind, how do you actually migrate a workload to EMR? What are the things that you actually need to think about? So the first thing we should really think about and talk about is why EMR in general. So there are 6 key points I think that we should talk about. So the first point is that it's really easy to use. You can launch a cluster in minutes versus the months or even years that it might take for you to do the same on-prem. To say provision a 100-node cluster or even a 1,000-node cluster on EMR is a couple of clicks of a few buttons, whereas on-prem that whole process may take you much, much longer. It's low cost, you can pay an hourly rate, and there's a bunch of flexible ways you can do this as well, say reserved instances where you can even drive down your costs even lower. There are 17 open source packages on EMR, and it's growing. And there's this perhaps conception that EMR is locked down in its own sort of proprietary world, but EMR actually uses open source tools, and the bits are equal. So if you're migrating, say, Hive or Presto or Spark from your on-prem environment, and it's straight from open source with no modifications, you can move it straight over to EMR with no issue. The fourth point is it's managed, fully managed. So you spend less time monitoring, and you can spend more time actually doing the things that matter, right? Having to work through, say, setting up a security configuration, every single node in your instance can be solved by using the capabilities that we offer. And it's secure, and we offer many options to help secure your cluster. If you want, say, Lux encryption, or if you want server-side encryption in S3, we offer all sorts of options for you to enable this for your environment. And ultimately, I think this is the most important one. It's very, very flexible. And by flexible, there's a bunch of implications that come along with that. By flexible, I mean that by using EMR, you can do a whole bunch of things in an agile and scalable manner. So for instance, if I wanted to experiment on, say, what is the best instance type for my workload, what I can do is spin up, say, 2, 3, 4, even 5 clusters, all with different instance types, and test out exactly which instance type is best for my cluster. If I were doing this in an on-prem environment where I needed to test out a specific node configuration, this frankly wouldn't be possible. Whereas in EMR, it's really, really easy to just click a couple of buttons and spin up different configurations of clusters and test them out. And it's this ease of experimentation that really lends itself to being able to do really, really cool things with EMR. For instance, being able to auto-scale your cluster on spot pricing lets you save lots and lots of money while still getting your ETL jobs done in a fraction of the time you would on-prem. So what are some key considerations and total cost of ownership considerations you need to think about when you're migrating? So the first thing to think about is do not lift and shift. If you have, say, a 20-node, 50-node, 100-node cluster on-prem today, it's not a simple matter of just looking at the specs of the nodes on your on-prem cluster and trying to port them directly over to EMR. While you can do that, it's ultimately not the best practice, because what you'll run into is that you're not taking advantage of the value prop that EMR is providing, what the cloud's providing. You've spec'd out your over-provisioned cluster and moved it directly to EMR. What you should be thinking about is how you can decouple your storage and compute using something like S3, where you're no longer bound to having this monolithic sort of infrastructure where when you scale up your compute, you scale up your storage. When you scale it down, you just scale down your compute. What this allows you to do is say, if I have all my data in S3, I can choose what kind of computer I want based on my particular workload. I don't need to over-provision my compute for everybody. I can focus on the workload, use the right tool for the right job. Instead of having, say, one big cluster that tries to do everything, I can have purpose-built clusters that are tuned specifically for the workload that I'm doing. The third thing to think about is you should deconstruct your workloads and try to map them to open source tools as much as possible. Try to look at the components that you could do, say, with Hive instead of some proprietary solution. Think about these kinds of things, because ultimately what this will allow you to do is save costs through licensing savings, and also allow you to really leverage the value out of EMR by being able to scale up and scale down elastically and apply this huge amount of compute to your workloads. The fourth thing to think about is how can you use transient clusters and auto-scaling? One common misconception is that EMR is only good for transient clusters. This isn't the case. Many customers actually use EMR for 24/7 workloads. Let's say you have an ETL job that needs to run every single hour. Many customers use an always-on cluster for that in EMR. So it's not the case that transient clusters are the only way to go for EMR. That being said, transient clusters are actually a really great way of saving money. So going back to that swim lane diagram from before, you saw that some workloads had significant gaps in between each time they were executed. If you spin up a cluster, if you spin up a cluster and have it run that workload for that time only, and then spin it down, effectively making a transient cluster, a transient workload, you can save that money that you would otherwise have wasted having it be idle. Another thing that you can do, and you really should think about, is how you can auto-scale. So for instance, going back to that 24/7 cluster, let's say that cluster runs an ETL job every hour, but during the workday, it's expected that the load will be very high, whereas at night, the load will be relatively low. What you can do is actually have your cluster scale up and down automatically based on the load on the cluster. So for instance, during the workday, my cluster could be 100 nodes large, and when it detects that the load is going down, it can gracefully shrink down and go down to, say, 50, 20 nodes, saving you money, ultimately. And the fifth thing to think about is carefully consider your instance types and try to leverage Spot as much as possible. The instance types are really important because you shouldn't be looking at over-provisioning anymore. You should be benchmarking through tools such as Ganglia to make sure that your instance is being utilized to the fullest of its ability and no more. By doing so, you're optimizing your own costs when you do so, while not sacrificing any performance. To that end, also, you can look at spot pricing, even saving up to 50%, even more sometimes, off of your instance price on demand to get your workloads to run cheaper, but at the same rate that you would ordinarily. One example of this is, for example, let's say you had an ETL job that you were okay with it potentially failing, you just needed to get it done today. What you could do is have it run on a spot instance. And let's say you had 20 nodes all in spot pricing. If it failed, you're okay with that because you can just bump up your threshold for spot pricing and run it again. This can ultimately save you a lot of money if you are okay with having the spot behavior on your cluster and your workload. You need to be able to translate your use cases to the right tools. So going down this entire chart, you can see that, okay, say for low latency SQL, there are tools to meet every single one of your needs. So low latency SQL, you have Athena, Presto, Redshift. For data warehouse reporting, you have Spark, Hive, Glue, or Redshift again. Management and monitoring, you can look at EMR console, Ganglia metrics. HDFS directly maps to S3. For notebook functionality, you can have Zeppelin or Jupyter via Bootstrap Actions. If you need a query console, you can use Athena or Hue. And for security, you can use Ranger through a Bootstrap template and CloudFormation template that we have, or Hive Server Tour or IAM roles. And there are many storage layers to choose from. It's not just HDFS or S3. EMR can actually talk to every single one of these layers you see on the screen here. So you can talk to DynamoDB, RDS, Elasticsearch, Redshift, Kafka, Kinesis. Every single one of these storage layers have a place within a big data architecture, and it's really important that you consider them. For instance, S3 may not be the appropriate choice when something such as RDS may be a better fit for your use case. I talked about decoupling storage and compute earlier, and this is a really important concept. In fact, if there's anything you take away from this presentation, it's that you should be decoupling your storage and compute when you're on EMR. And you can do this by using S3 as your data layer. So S3 is our object store service, and it's designed for low latency durability, and it's massively scalable. And effectively, you can use it just like you would HDFS. If you have a workload that's currently in HDFS today, you can just point it at S3 instead and work just the same way without you having to change anything in your code. What this allows you to do is, in fact, say if you had, say, 4 clusters on-prem that had all that same data set but different workloads, you could save a lot of money in storage by putting this data set into S3 and having your clusters, your multiple clusters, point against this data set in S3. One example of this is actually HBase and S3. So FINRA saved 60% of their total costs of HBase on EC2 by moving to HBase and S3. And what this allowed them to do was effectively save tons and tons of money on having to rehydrate their cluster in an event of, say, shutdown, refresh, things like that nature. Being able to think about storage in this manner really allows you to think about really, really cool new architectures. The utility that comes and the cost savings that comes from thinking in this way can't be understated. So let's talk about a couple of tips about using S3. So the first tip is avoid using key names in lexicographical order. What that means is essentially if you have, say, a file name that starts with an A, and you have a bunch of them that start with an A, that's actually something that you want to avoid. You want to introduce entropy into the beginning of the key at all costs, because what that allows you to do is spread out the load on S3 evenly and avoid hotspotting. So to do so, what you can do is, say, stick a timestamp in the front of the key name, or some random hash value in front of the key name, such that you can avoid hotspotting. The second point to look at is improve your throughput and S3 list performance whenever you can. So one way you can do this is actually using EMR consistent view, where list performance is improved dramatically by instead of issuing list requests directly against S3, what EMR will do is actually issue the list request to DynamoDB, which results in much faster list performance. Another thing that you can look at is using compression on your data sets to minimize bandwidth from S3 to EC2. You will save a lot of time and effort if you use a good compression format on your data sets. Especially in the Hadoop world, splittable compression is really important, because you need to make sure that every file is optimal size for every node in your cluster. And if you have it splittable, the cluster will be able to handle this for you. Commoner file formats like Parquet can also give you increased performance on reads. So if you're looking at a format, say, like Parquet or Orc, I encourage you to dig really deep into that, because these kinds of file formats can give you huge performance benefits. So going back to that TCO analysis on the swim lane, you notice that the circled things are all sorts of different clusters, right? You have a daily reporting ETL job that takes up 6 hours, but it only happens once a day. That should be a transient cluster. You have an analytics cluster that runs for 2 hours throughout the day. Again, that should probably be a transient cluster. Whereas that NoSQL workload that you see all the way at the bottom, it goes on throughout the day. You shouldn't make it transient. It should be a long-running cluster. Another common question that we get is, how do you submit a job? Is it just a matter of doing it just like on-prem? Or is there something that AWS and EMR kind of control and keep you from doing so? And the true answer is that you can actually do both. We do not limit you. You actually have full super user access to your clusters, your root access. But we also provide various mechanisms for you to submit jobs to your cluster to make your life easier. So there's the EMR Step API. You can submit jobs to AWS Lambda, or our serverless compute service. You can actually also use AWS Data Pipeline to have a cron-like job run against your cluster. And you can also use third-party things such as Airflow or Luigi or other schedules on EC2 to get the same thing going. Let's talk specifically about hardware optimization and performance around that. So a couple things to consider. When you're looking at your hardware, you need to really consider, okay, is this going to be for a transient workload or a long-running workload? For a transient workload, the node type matters less in terms of the storage, right? And even to a certain extent the compute, because what you can do is modify and fiddle around with the parameters such that you get your job done in the amount of time you've allotted for the transient job to execute. Whereas for a long-running cluster, you probably need to think about it in a sense where, okay, this cluster is going to be on pretty much 24/7. How much storage should I allocate? How much memory should I allocate? And I should be planning for this kind of usage. And we have a huge variety of instance types that lets you really fine-tune how you're going to set this up. And it's not really just a function of instance types as well. You can also do things with cluster size. So for certain applications, such as the HBase and S3 example, it's actually more performant to have a bunch of smaller instances, say an M3 2x large, running that workload versus a few vertically larger instances. For a couple of reasons. The caching for, say, the HBase block cache, things of that nature, where more smaller nodes is actually more performant than a couple of really, really fat, strong nodes. And the last consideration to think about is, okay, and I talked about this briefly before, file formats, say, are you using compression? Are you using a splittable format? Are you using, say, gzips, or are you using Snappy? Are you using Avro, Parquet, Orc? What are you using? Think about it and make sure that you clearly enumerate exactly what you're using, why you're using it. There's also a huge wealth of on-cluster UIs to really, really quickly tune your workloads. And thankfully, they are typically bundled with the application you're using. So for, say, managing applications such as Spark, Hadoop, Tez, HBase, Flink, each of those applications have their own special UI. And the sense of, say, administrating your cluster or designing queries or looking at, say, notebook functionality, you can also run these all in EMR as well. I talked about this briefly as well, but one of the most important things that you can do is optimize around cost while still meeting your SLA. So I talked about Spot briefly, but also you can use reserved instances to do the same thing. When you use the two together, what you can do is, say, have your core nodes on EMR be under reserved instances, which will meet your core SLA, let's say your minimum SLA for your workload. And then typically your minimum SLA is really not what your users want. Your users want the workload to be done as quickly as possible. So what you can do is actually use Spot instances to speed up your workload. Let's say you have 20 reserved instances for a cluster and you add on 100 Spot instances to speed it up. By doing so, you have this really, really flexible architecture where you're guaranteed that the job will run in a certain amount of time, but using really cheap compute, we can get it done in a much faster time frame. A new feature that recently came out is actually instance fleets. And what this is it's a way for you to have a variety of options intelligence around how to provision your instances. You can now provision a list of up to, I think, 5 instance types with corresponding weighted capacities and spot bit prices. So what EMR will do is automatically provision on-demand and spot capacity across these instance types when creating a cluster. This can make it easier and more cost-effective to really quickly obtain and maintain your desired capacity for whatever cluster you might be running. What you can also do with this is also specify a list of AZs, and EMR will automatically launch your cluster in one of those AZs. EMR also actually rebalances your cluster in the case of spot instance interruptions by replacing instances of any one of the available types in your fleet. And what this ultimately allows you to do is make it easier for you to maintain your cluster's overall capacity. So you can use these instead of instance groups, and it really just looks like any other group, like a master, core, and task fleet. So we also talked about autoscaling briefly, but I really want to focus on it right now as well. You can lower your costs with autoscaling with little management on your part. Traditionally, before we had autoscaling come out for EMR, what you would have to do is scale your cluster up and down manually by, say, gathering metrics or figuring out, say, at 8 a.m. and 5 p.m., we need to scale the cluster up and down accordingly. What autoscaling allows you to do is actually do this all in an automated fashion based on certain criteria. So instead of having to do it yourself, we've made it easier for you to scale up and down your cluster based on predefined criteria and ultimately save you money. So I've talked a lot about infrastructure and instances and optimization around, say, instance types. But a question that often comes up, especially as Hadoop is getting more and more popular among the enterprise segment, is how can we leverage and take advantage of the great cost savings and flexibility that EMR provides while kind of still maintaining encryption and access control? Configuring these things in the Hadoop world can really be kind of difficult, and we've been constantly iterating and making it easier for our customers with EMR. So for an encryption point of view, EMR supports at-rest and in-flight encryption. At-rest encryption is supported across all engines, and for in-flight encryption, we support TES, which you can use with Hive and some other things, Spark, and MapReduce. In the near future, we will be supporting things like Presto, HBase, and Flink for in-flight encryption. One thing to consider is that when we're looking at encryption, you need to make sure that the engines in question have encryption built in. EMR has 17 open source projects now, and not every single one of these projects has these features built in for open source. So it's really important that you understand what you're getting into if you have strict encryption requirements. From an at-rest encryption perspective, we support S3 server-side and client-side encryption with the goal that we integrate with how any client would push anything to S3. It's the same envelope encryption for client-side and the same server-side encryption for server-side. For local disk, we encrypt the full disk as well. So you can get more info from the docs, but configuration is pretty simple. We have this concept called security configurations, where you just tell us the keys to use, and we encrypt everything for you and do really what we say in this slide. Really simplifying the painful and manual process of setting security up on your Hadoop cluster. The last thing I really want to point out is if you want to make sure that you're covering encryption to the fullest extent during your migration process, you need to look through the different storage layers that your data gets written to during a typical workload. So S3, HDFS, local disk, memory. How are these distributed frameworks shuffling their data around, and how is it encrypted? Those kinds of things you really need to think about, because you can say only encrypt at rest, but you're exposed for in-flight. Or you have a spill to disk, and that's not encrypted. So these kinds of things you need to really consider. So EMR supports IAM policies. And for those who don't know, IAM is a service by AWS that enables you to manage your users and their permissions within your account. And what you can do is you can use IAM to create user-based policies and attach them to users. And what these policies ultimately do is grant you deny permissions and determine what actions a user can perform with EMR and other resources within AWS. So for example, what you can do is you can allow a user to view EMR clusters in an AWS account, but not create or delete them. In addition, you can say tag EMR clusters and then use these tags to apply fine-grained permissions to users on, say, individual clusters or a group of clusters that share the same tag. So if you look at the slide, you can see that there are specific actions that are allowed within the policies. And you can do things like apply condition elements to specify fine-grained access control based on cluster tags. EMR doesn't support resource-based and resource-level policies, but the condition element can really give you the fine-grained access control that you need. So let's talk about authentication authorization within the realm of security and EMR. So when we're talking about authorization and authentication, we typically break them down into two different levels. So one of them is at the EMR and API cluster level, and at the per framework and per application level. Things are a lot easier when you have a single tenant cluster. You have a cluster that comes up, runs a bunch of jobs, and shuts down. No one logs into it. You can think of this as really a single tenant system, and the full cluster authentication authorization are pretty simple and easy. So in EMR, to do this, we use IAM roles. You have to give the EMR service an IAM role, and then you can give all the EC2 instances that are part of your cluster an IAM role. That role determines what S3 buckets in your cluster can access. If you can access DynamoDB, can't you access it? And we use a managed policy by default that dictates which services EMR has access to interact with. What we found is that security-conscious customers define a custom policy to have fine-grained control over what the EMR clusters can talk to. We also support tag-based permissions to allow certain IAM users or federated users to have certain access to clusters. If you want to SSH into the cluster, you can SSH in, and you really have root access to the cluster. So it's pretty simple from a single tenant perspective, but with multi-tenant kind of stuff, say a typical on-prem environment with tight AD integration and something like Hive to EMR, you're kind of at the whim of what each app framework supports. Like I said before, EMR uses open source bits. So if you're running Hive Server 2 on-prem and you're sitting with a bunch of SQL standards-based authorization, you can do the same thing on EMR. Some customers don't really realize that there's parity between both of those. Today you can use LDAP authentication with Hive Server 2, Hue, Presto, and Zeppelin. And you can configure this through security configurations, and a bunch of customers do this today. This allows you to connect, say, via JDBC, log in, have access to SIM tables, and have access to others. And coming in the near future, we're going to have Kerberos support and give you the ability to run a KDC locally or use Active Directory as a KDC and support the service principals and everything else that you would need to create a trust to get users from AD to somewhere else. Another thing that we're getting is storage-based permissions into EMRFS, our proprietary connector to get data from S3. Today, all the calls that you make to S3 are under the EC2 role, but if you have, say, 10 users in a cluster, you may want to make have some of them assume one role and have some assume another role. So we're building that kind of storage-based authorization into EMRFS for that use case where you want to have authorization against stuff in S3 versus something more SQL-based, like, say, on a table. So one tool that's really new to the EMR ecosystem that comes up for a lot of customers is how to use tools such as Sentry and Ranger with EMR. It's similar to, say, Hive Server 2, the functionality, but the user experience is much better. There's a UI, it's easier to manage, there's auditing with Solar, and you can find this on EMR today. There's a post in our big data blog that has a cloud formation script that lets you create an EC2 instance running Ranger. So if you're interested in this, go ahead and take a look on the big data blog to do so. And to kind of sum this up, we have a few more things to talk about. So for, say, governance auditing, there are a couple of tools we see people using, but there's not really one tool yet. There are partners out there such as Data Guys and Bluetown that you can use in conjunction with EMR to get kind of this detailed, fine-grained use case. But within our own services, we do support CloudTrail logs for EMR APIs. So you can see who's creating clusters, who's interacting with the clusters, say via steps. Another thing you can do is monitor S3 access logs, which clusters are hitting specific objects, and who's say touching groups of objects within S3 based on those logs. You can also say scan your typical Yarn app logs, the same one that you do on-prem, and EMR exposes these logs to you. And if you need to, say, do application level auditing, Ranger, I just showed you that a slide ago, and you can use Ranger to do that sort of thing. So in the interest of time, there are great customer stories out there, but I do want to give time for questions and Q&A. So both of these user stories, FINRA's as well as DataZoo's, they have great customer stories out there on top of, say, SlideShare or YouTube that you can look at, where they talk about how they save 30% improvement on their infrastructure versus Greenplum in the case of FINRA on going to EMR, or for, say, in the case of DataZoo, how they process 2 petabytes of data daily, and they run 24/7 and really make this really, really cool infrastructure where they process for their big data. So with that all said, let's go ahead and go to Q&A.